Okay. Okay, we are sharing the screen and therefore we can go here. Now let's do the slideshow. Perfect. Okay, do you see everything? Oops. Do you see the first slide? Thank you, Davide. Okay. Okay, so, well, let me do this premise. Prolog contains, it's a programming language, right? But it's a programming language which is based on logic. So it is very different from any programming language you have seen so far. And actually, from past experience, sometimes students that are not familiar with programming language get it easier or find it easier than students with a programming background, okay? Because the formulation of algorithmic solutions using logic may turn out to be quite different and to some extent a little challenging. Now, the goal of this section is not really to provide you with another language to use in production, so to speak. It's rather a theoretical tool which can also be used in practice. Actually, we are going to use full-fledged systems, and I've been using also Prolog implementation in our intelligent robots. And but on the other hand, it is not something that is taught in this course because you are going to use it directly as an engineer. It's unlikely. I'm not. I am perfectly aware. But on the other hand, I think it embeds all the modeling elements that we've been teaching throughout all the course, because you have to have a search model in your head in order to understand the execution of a Prolog program, and you have to provide a representation in a knowledge representation language of your problem. Okay, so for these two reasons, we are going to develop Prolog, and it's a small section of the course, and as I said, is something which is in a sense completing and closing all the notions that we've been teaching in the course. Some students find it hard. Some students, since it's a small part, decided to skip it. I mean, that's up to you. Of course, you can skip this part as you can skip any other part for what I'm concerned. And the only thing is that maybe this is a little bit more self-contained. It is connected with logic, but I'm not suggesting to skip, but it is self-contained, and the skipping it will not endanger the other sections of the course. The final reason why I am doing this Prolog, it's because I find programming in Prolog, I find it one of the most intellectually stimulating activities. And as a matter of fact, one of our goals is to make sure that in addition to the neurons in the neural networks, you use very well also the neurons that are in your brain. And therefore, this is a very good gym for your neurons, I think, especially in the flavor of programming. So I'm still having a great pleasure in doing Prolog programming, and I wish I could do more. Okay, having said that as an introduction, let me, before we enter in the details of the language, let me give you all some background. Okay, first of all, what is the idea behind logic as a programming language? Or as a representation language. The difference will be maybe clearer later. The language is to a large extent the same, but in fact, in order to get a very efficient reasoning, we compromise with some of the features that are required for reasoning, namely completeness, first of all, and secondly, for some features, possibly also correctness, okay? So, but we will discuss this later on. For what the language is concerned, the language is a representation language, okay? And what is the idea? Well, seen from a logic programming point of view, is that the program contains the description of a problem, say the knowledge base, where in the knowledge base you put all the assumptions that you need in order to obtain a solution for your problem. And then you have the execution, which corresponds to proving that something follows from your knowledge base, where hopefully the solution to your problem follows from the knowledge base. So the point is that the solution of the problem will come up through the inference and the problem specification. And therefore, Bob Kowalski, which is considered one of the two fathers of this programming language, invented this equation, which says that what is an algorithm? It's logic plus control. So the emphasis here is on logic, on the logical specification. So one example that we will see, not immediately, but maybe next class, is, for example, a sorting algorithm where you take the definition of a sorted structure, and from the definition itself, you can have the inference can generate for you an algorithm that does the sorting. Now, this is an ideal, as you can imagine, and in fact, in some cases, the solution which is provided is not the most efficient one, but on the other hand, it's something that can be used for prototyping, for thinking about the problem, and for finding the correct specification, the correct model of your problem, which once again, it's the aim of this course. Okay, so let's move on this introduction. So we are using a tool. I do recommend that you download this PROLOG or any other PROLOG, I don't care. This is particularly easy, and it's the one that I will be using, but any PROLOG would do, okay? This is called PROLOG. It's an open software. It runs on every platform that I know. By the way, there are also systems where you can do the development online. Okay, so you don't have to have a PROLOG on your system. You just have your everything in the cloud, including the program execution mechanism. I am old-fashioned and I like to have software on my PC, because sometimes I do when I'm not connected, I do programming when I'm not connected to the network and interrupted by many other things, but that's my personal view. There are many resources, many textbooks, any resource, any textbook will do. The best PROLOG book, for sure, is this old book that you may still be able to find in some libraries. And some of the examples that I'm using are taken from this book. But here is one other example of a resource. I hope it's still there. I haven't really checked. But as I said, any textbook on the language will do, or any resource that you find on the network, because we are not going to go into many implementation details. We look only at the principles that are behind this language. There are applications. When there were expert system PROLOG that at some point became very popular. Actually, it was chosen by the Japanese as the 5th generation computing system program launched at the end of the 80s. So maybe many of you were not born at that time. So from this point of view, it's an old language, but if you look at programming languages, with very few exceptions, most of them were born at the beginning of the development of computer science and artificial intelligence. Anyways, I already made the disclaimer. This is not to be viewed as a programming language. This is going to be viewed as one practical tool for practicing and experiencing the ideas and concepts behind this course. Okay, what is the idea? We do essentially the rules of the problem. Well, just to make an example, you give the rules of chess, and then you get the program that can infer what is the best move, okay, without including any heuristics or anything else. That's not clearly applicable to PROLOG, but we will see what rules are for our problem specification. And then we can, the execution of the program corresponds to asking for the evaluation of a query, or which essentially asks whether the query is follows from the program, where the program is the knowledge base and the query is our alpha. And we will establish the correspondence between PROLOG computation and resolution at a later stage. But the idea is that the system will be able to answer the query, and the answer of the query would be obtained by checking entailment from the knowledge base or the program, as you like. Okay, so here is our classical example, or men are mortal, Socrates is mortal. What is the conclusion? Socrates is mortal. How do we formulate this in PROLOG? Well, the syntax may sound a little bit, may look a little bit odd, but it's, it's been defined long ago. And, syntax is something that can be changed arbitrarily, because it's, in a way, you could even choose for a programming language your favorite syntax and create your own parser. But in the end, syntax is something that we learn, and it sticks in our minds. And therefore, the syntax of PROLOG has never been changed. So here is the definition: all men are mortal, which would be an implication where we say that if X is a man, then X is mortal. So we will see that, in fact, this symbol here is like the arrow. Let me try to draw the arrow to show. Okay, if we want to draw the arrow here, we have to say that this man implies mortal. We have a variable here, which is something that we have not seen yet, and we will we'll give a full account of how variables will be treated when we have done first order logic, namely next week. But for the time being, we can use these variables intuitively. So we say that this is a rule, meaning that we can replace X with every individual, okay? So we say that for every individual X, if X is a man, then X is mortal, okay? So this is the implication: man, mortal. And then we have the fact, this is the terminology of Prolog, that Socrates is a man. So by these two things and by modus ponens, we can indeed derive that Socrates is mortal. You see the implication, the modus ponens, once you have this implication, this is one of the two premises, this is the other premise, and this is the conclusion. Well, Prolog is not directly telling you the conclusion, but you have to ask for ask a query. And the query that you ask is that, is it the case that Socrates is mortal? Does mortal Socrates follow from the program? And the Prolog system will answer yes or no. Okay, in this particular case, given that program, it will answer yes. Okay, please, in particular with this notion with Prolog, introduction with Prolog, ask questions, okay? This is one of the classes where if you get lost at the beginning, you will be lost until the end with few options, few chances to recover. So if you are stuck with something that I say, please ask questions. Okay, so if there are no questions here, let's move on. So how do we build a program or knowledge base? Well, in the end, the program is a set of clauses. And in these clauses, we distinguish two types, exactly the same two types that we have seen for Horn clauses in the first definition. Because look again at this example, we have one implication, this is a Horn clause, and we have the one symbol, okay? In this case, we call it atom, because it's not just a symbol, but it's a symbol with an argument. But any symbol with an argument stands like a propositional variable in the first definition of Horn clauses that we have seen. And this stands as an implication. So in fact, we can also have more than one condition in the antecedent, which is going to be on the right-hand side of this rule. So here is an example of a rule, and here is an example of a fact in Prolog terminology. Oops, I don't want to start that. So, for example, we're going to have an example with the family. I anticipate that I'm going to speak about my family, so you know a bunch of names about my family. And if you want to understand something with the first Prolog programs, it is much better if you create a little program with assertions or facts about your family. At least you know what is going to be expected from that knowledge base, so to speak, because the family names can be a little bit misleading, a little bit confusing. So in this case, my son is Jacopo, and therefore I can write in my program a fact like Father Daniele Jacopo. Okay, this is a piece of Prolog syntax. Notice that every rule or fact is concluded by a full stop. It is possible to use the facts including variables, but we will not pay much attention to them. So the important thing is that this slide is that the fact is an assertion like this one, okay? Atom, namely predicate symbol, followed by arguments which are specific individuals in our domain, okay? Notice that a convention in Prolog is that names of predicates and constants start with a capital letter. It's the other way around. The names of variables start with a capital letter. Here is a lowercase letter, not a capital letter. I will double check and correct this one. Okay, so let me clarify. This is a predicate name. This is a constant, according to the terminology here. This is a constant. This capital X, this is a variable. Okay, so I will correct the slide and give you the correct reading. Okay, so here is the first piece of syntax. We are almost done with the definition of the language, believe it or not. We only have to specify what is a rule. So as I mentioned, a program is made by rules and facts. We have seen what facts are. Now we see what rules are. Rules take the following form. A, if, B, C, D, okay? Where, as I mentioned, I showed in the example, this symbol is, in fact, should be read as an implication in the reverse direction. Namely, B, C, D imply A. Is the dot at the end of the line mandatory? Yes. Okay, so, but we can also read this rule, A is true if B, C, and D are true. Okay, but notice that if B and C are true, then A is true. So the reading is, let me write again, just to make sure that there are no doubts about this. We have here an implication like this. Okay. Now,
sorry, I have a question. Can I?
Sure.
Commas are standing for and.
Commas, yes, but it's
Okay.
like you can see them again as a set, or in this particular case, the set is interpreted as a conjunction.
Okay.
So this is actually, remember that you have that the first definition of on clauses was with the A1, AN in the antecedent, and B, one single propositional symbol in the conclusion. Now, here we have the same form for the rule, except for this different syntax. And the other difference is that A, B, C, and D, they are not propositional symbols, but they are atoms. What are atoms? Atoms are predicate symbols applied to arguments. Okay? And what are arguments? In our simple initial case, arguments can be two things. They can be either variables, and in that case, they are written with capital letter as initial, or they can be constants, and in which case they are written as a lowercase as the initial. Okay? The general form of a predicate, therefore, is this one. And in this particular case, we say that without function symbols, we consider that the arguments of a predicate, that, as we will see later, will be called terms in general. They will be either constant symbols or variable symbols. Okay, we have said everything we need to say about the syntax of the language, almost. There is only one more thing that we will see in a couple of classes. Any questions so far? What have I done? Ah, yes, I stopped the presentation, but I need to go back to the presentation. Okay, let me clear. Okay, here is the example of a program. Let's see. Whoops. It's moving too fast. Things are running out of control, but do not worry. We will going to regain control soon. Okay. You had a preview of all of our slides for some reason. Something happened with this program. Be patient. I will get back to you shortly. Okay. Okay. Now we should be back functional. Okay. Okay, here is our first example. We want to define the program for grandfather using the PROLOG terminology. So what is the grandfather? The grandfather is either the father of the father or the father of the mother. Okay, so in PROLOG terms, we can say that if X is the father of Y and Y is the father of Z, then X is the grandfather of Z, right? Similarly, if X is the father of Y and Y is the mother of Z, then X is the grandfather of Z. Anyone, any comments on my reading of this? Okay, it should be straightforward, right? Now, in order to use the mother and father relationship that I was using as facts in my program, we need another rule. What does it mean that X is the son of Y? Well, that either Y is the father of X or Y is the mother of X. So in this program, we have two procedures. One is the procedure grandfather, and one is the procedure son. Okay, and these are rules, as you can see, because they have an antecedent and a consequent. By the way, let me introduce a little bit of terminology about the format of these rules. These are the premises, and this is the conclusion, or this is the head of the rule, and this is the body of the rule. Okay, so we call them rules. We call them clauses. The reason is that this is indeed an implication, and it's an implication which takes the form of a horn clause. Okay, so rule, clause are synonym in this case. Well, clause, not literally, because clause is more general since it encompasses both facts and rules. Okay, so are we fine with these programs? Okay, we need to see the execution of these programs, okay? Well, how do we start the execution? We start the execution with a goal, by specifying a goal. Actually, the PROLOG prompt is a question mark. And you can specify a goal by asking the system whether a bunch of atoms follow from the program. Normally, the queries can be formulated as bunch of atoms. So this is the general form of the query. But in fact, we will very often use only one atom as the query. So given the program, we want to know whether Daniele is the father of Jacopo. And we ask this query. And what does the PROLOG answer? It will answer yes. You may say not really no big deal at this point. And in fact, we still need to see what is the power of PROLOG as a programming language. Well, father is just like checking a fact in a database, right? So we have the relation father, and we check whether father belongs is a tuple this is a tuple in the database. But we can do much more. Here is my, you will learn about my family. I have a question. It's not the opposite. The opposite of what? I don't understand the question. Can you please speak up or clarify the question? No, Daniele is the father of Jacopo. No, I mean, there is no rule. We can read the arguments as we like. Okay, but in this, I will try to keep the reading such that this is the subject of the relation. Okay, Daniele is the father of Jacopo. And this is not, as I said, this is only a convention. It's not really mandatory. I could have defined the relation father exactly the opposite, okay? But just for avoiding confusion, typically when we say father Daniele Jacopo, we mean that Daniele is the father of Jacopo, okay? Okay, good point though. Now, here we have, as I said, you will learn about my family as we go. I don't have to explain it now. Well, remember we had not only father and mother, we have added a couple of other facts concerning my son and my wife. They're both nice. Okay, and about the gender, and we can say that Michela is a female gender. Okay. Now, at this point, we see that we can use also variables in the queries. So instead of just checking whether a tuple is in a database, we can also use as a Prolog as a query language, and we can ask, is there anyone in your database of facts that is nice? And we ask this by using a variable in the query like this. And Prolog will answer, yes, Michela. Now, one thing that Prolog can do is that can provide more answers. So if you want more answers, after the first one, you type semicolon, and the Prolog system will provide you with another answer until there are other answers available. Okay? Then let's see what can you do also with variables, which is, again, we're still to a large extent looking at the databases. Okay, let's first look at this first part. Grandfather Heriberto X. What is going to be in your, in this case, the result of, well, same as before. We are searching, or we are asking our program or knowledge base whether there is an X such that X is the, Heriberto is the grandfather of X. Okay, so now in order to do this, Prolog will have to use the program grandfather and go into the set of facts and check first that there is a fact for Heriberto and some other, a son of Heriberto, such that the relation father Heriberto X, father Heriberto with this person is satisfied. And then remember the definition, we have that X is the grandfather of Z if there is a Y such that X is the father of Y and Y is the father of Z. Okay? Now, in this particular case, X will succeed. So one answer that Prolog will be able to return is that X equals Michela follows from the knowledge that is in our knowledge base, because Heriberto is my father and I am the father of Michela, and this is written as two specific facts in our program. Now, in this particular case, we have that we have a conjunction here, and when we have a conjunction and we have variables, we have that the same value that is found for the variable X here should also be used for this other variable X here. Okay, so if we find that, for example, Michela follows from the program, name from grandfather Heriberto Michela, then we should also check whether Michela is nice. And in fact, we have already seen that Michela is nice. So the answer to this query will be yes, Michela, just as before. But in this case, the system is doing two more things. First is using the relation grandfather and finding that Michela is the grandchild of Heriberto, and then checking that the same individual that here is found to be the grandchild is also shown to be nice, or it's in, we can also see that it's nice in our program, okay? And we can have two variables. What is going this query be returning?
Professor, excuse me, I have a question.
Yes, go ahead.
But in the previous, when we said that X must be the son of Heriberto, if we don't have that X is nice, the program will return no.
Careful, careful. Let's look at the two one at a time. First of all, we have grandfather Heriberto X, right? So the X that will be returned will be an X such that the X here corresponds to this second argument, right? Which we find here. We have grandfather Heriberto X. Now, don't be confused by the fact that we're using X in both places. So that X is just another variable for us. So this variable goes in the second position of the relation grandfather, and which corresponds to this Z here. So in order to find, to check for the relation, we have first to check that X, namely Heriberto, is the father of some individual Y. And then this Y is the father of Z. Once we find the Z, then we can return grandfather Heriberto Z. Are you following?
Yes.
Okay, good.
Yes, but my question was, if we don't have nice Michela in the data set.
The answer will be no.
Ah, okay.
They have both to follow, both the two atoms they have to follow, and they have to follow with the same value for X.
Okay. Okay, thank you.
You're welcome. So here is another example. In this example, we have two variables. Let's forget the nice Z at this point, but to focus on the two variables. What kind of answer are we expecting here? Any guess from the students?
Should be yes, should be un yes, Heriberto Michela.
That's one answer. Correct. Any other answer if we use the semicolon? Well, in fact, the answer will be all the pairs of people that, according to what the facts that we have in the database, satisfy the relation that there is between the grandfather and the grandchild. Not all entries from the database, as someone suggests, but all the pairs of individuals X, Z, such that the relation grandfather can be satisfied with the entries in the database. Okay, we will see this in a second. Let me see if, yes. Let me now move from this. Oops. Let me keep the chat on and let me stop the presentation here. And then let me go here. And then let me go here. Okay, so here is the Prolog file. Can you see this? Yes, okay. Here we have two windows. In one window, I have my Prolog program, which is this one. Okay, you see all my family with the father, the mother, and so on. And you see here at the bottom, the relation grandfather. Okay. Now, here on the left, we have simply, let's see. We have a window, which is a shell window. Where that I position in the location where I put my program. Okay, so from here I can start my Prolog system. And the Prolog system is asking me, what do you want me to answer? Before doing anything with the program, we need to load a program, okay? Because without any program, we cannot do much. So my program is called like this. And this simple command allows the system Prolog to acquire all the rules and all the facts that are written in this file that you see in the editor on the right side, okay? If there are no syntactic errors, the program answers very kindly true. And at this point, it knows about my family. So if I ask father, Daniele Jacopo, it will answer true, right? If I ask father Daniele X, it will answer yes for Michela and the for Jacopo. If there are no more answers, it will return to the prompt. Okay, so now I can practice also with the relation grandfather. So if we want to see grandfather, oops. It will find all the grandfathers of all the grandchild of Heriberto. Let's first do Michela. And this is it. We see that there is no other option here. If we ask X, we're going to find Michela, we're going to find Jacopo, we're going to find Lorenzo, and so on. All that are defined based on the relationship that I have in my program. Okay. Now, are we happy at this point? Can we move on? Okay, let's go back to this, to the slides, and here we move to a difficult case, a more difficult case, because here we are going to consider a relation which is a recursive relation. After all, we have defined the relation grandfather, which goes 2 levels in the family hierarchy, so to speak. We generalize and we want to define the relation descendant, which can go an arbitrary number of levels in the hierarchy. Okay, But so how do we define that X is a descendant of Y? Well, first of all, if X is the son of Y, or we can say that X is the descendant of Y if Z is the son of Y and X is a descendant of Z. Okay, so considering that Y is the ancestor, we take one son of the ancestor and we check whether the son of the ancestor is in the relation descendant with the original X. Okay, so let me clarify. Maybe X is the descendant of Y, right? So X is at the bottom of the family hierarchy, and eventually Y is at the top. They mean the old generation. So how do we check this relation? Well, we have to find a Z such that Z is the son of Y. So Y is the ancestor. Z is the son. And then we have to check whether X is a descendant of Z. Okay? So if we do this for 2 levels, we find that we have the son relationship twice. If we have more levels, we have to repeat an arbitrary number of times the relation descendant. So here we have the same syntax, but we have a recursive rule. Okay? And in fact, we can use the recursive rule, this recursive rule, in order to prove that Michela is a descendant of Heriberto. The same as notice that in order to do this, we need also to add that the relations on between X and Y is satisfied if Y is the father of X or Y is the mother of X. Okay, so if we go back to our program, we can check this. Here in the program, we also had the relation, so we had descendant Michela Heriberto, which is true, right? And well, I pushed something wrong. Exit. Okay. So here that's the program. Let me show you another thing which hasn't come up yet, but let's see whether we find it on the slides first. Well, yes. I have to say this now. Just go back here. So what happens if I say, let's start with a simple case, grandfather X Michela. What are we going to get? Okay, we can use the variables in any position that we find. What does the 1, 2, and so on denote here? I'm sorry, I'm lost. Where? I mean, these are comments. I mean, in this slide, right? These are comments. I'm just using this percentage as a comment in the line. So anything beyond the percentage is nothing that concern with the nothing that has to do with the rule. Okay, and here I'm going to use it in order to number the lines for explanation. Okay, so I wanted to show also the multiple use of variables. And then, as I said, if we say grandfather X, Y, we are going to find all the pairs. In this case, Heriberto Michela, Heriberto Jacopo, Heriberto Lorenzo that we see, but we can also find my grandfather, the grandfather of my brother, the grandfather of my other brother. Okay? So that's already much more powerful than a function in a programming language. Okay? Now, let's move on. Are we only computing only with the family? Not, certainly not. We can very simple define a graph and then define a procedure for traversing the graph. So here we have a graph where we have that is lowercase letters denote the nodes of the graph, and this is an arc between the two nodes in the graph. Let's see whether I can draw the graph. So here we have a node. This is A. Then we have from A an arc to the node B. Then we have an arc to the node C, right? Then we have an arc from B to D. Then we have an arc from D to E. And then we have an arc from F to G. Okay? This is the graph represented here. Doesn't really matter which is a connected graph, okay? But on this graph, we can define very simply, a relation for traversing the graph. And we define this by checking whether a node is connected with another node, okay? So we say that the node is connected with itself. And then we say that the node is connected with another node if there is an arc between the first node and some intermediate node, and this intermediate node is eventually connected to the node 2, okay? So in this way, we can use the relationship connected in order to check whether there is in other words, whether there is a path between two nodes in a graph. And this is essentially a very similar definition to the one that we have seen, because the relationship, a family relationship, is a special case of a graph. Okay, so we define the graph through the relationship in the tree, and then we can compute connectivity among the nodes. Okay, so here, if you want, we can check. I have already, I think that this part of the program was already, we can say whether it's connected A with D. Oops. Then we need to load graph. I forgot the column. Okay, that's it. Okay, we have it. Now we can say again the connected, and this is going to be true. There are multiple paths between A and D according to our graph structure. Let's see. Yes, because there is also something that we had forgotten here, which is this connection here. Okay, thank you. That's it. Okay, so the nice thing is that we can also find between with this to reach all the nodes that are connected with A, that are reachable from A. So that's A, B, C, D, E, C, D again, E again, and false. And similarly, we can also find all the nodes in the opposite direction. So all the nodes that lead to have a path from them to E. So E itself, A, from A we can get there, from B we can get there, from C, from D, and so on, okay? And if we use both variables, we find all the pairs of nodes that are connected, okay? So that's the meaning of this program, which essentially, you see, it's 2 lines to write a program that is is checking a path between 2 nodes in the graph. This shows how powerful it is. Can you imagine how much you have to write in terms of data structures and in terms of algorithms in order to do the same thing in a conventional programming language? I hope that this description of a operation on a graph makes you speechless concerning the power of the language. Okay, but let's move on. Okay, we have seen these multiple roles, we have seen connection. Now we have to see how the system works, okay? So now be focused, this, few more minutes before we finish, but I will explain in 3 slides or slightly more, how is the computation model behind PROLOG, okay? We are going to define 3 elements. The abstract interpreter, what happens when, what does the PROLOG system do when answering your query? How does it do the search for the solution? And then one aspect that we are kind of postponing to the next week, which is how are the variables treated, okay? This is something that we will be skipping in this first presentation of the language, and we will go certainly in greater detail next week. Okay, so let's start by considering the aspect of variables. Okay, I will skip a couple of pages with definitions that will become more understandable soon. And let's look at what does it mean to have a unification between 2 expressions, which is represented by this predicate here, unify. 2 expressions are of the form, are 2 atoms, in fact. First atom is PT1Tn, the second atom is PS1Sn, okay? So the idea is that we want to find one, whether there is a substitution that makes the 2 atoms identical. So let's look at the examples, and for the time being, let's focus on the examples. And then, as I said, next week we will do a much more detailed treatment of this. So first example, what kind of substitution do we have to apply in order to make this first argument identical to this first argument? Well, there is only one possibility. We can replace X with A. Notice that we can only replace variables, okay? Other case, what can we do here? We can replace X with Y. In this case, we will obtain P of Y and P of Y, identical. Can we unify Q of A with P of A? The answer is no, because there is no substitution that allows us to make P identical to Q, okay? Now, what about the P of X, B and P of A, Y? This is a bit more difficult because we have variables on both atoms. Now, P is the same, so we're fine. So we can take A to replace X with A, and we can replace Y with B. In this case, we obtain P of AB, and also in this case, we obtain P of AB, because X is replaced by A and Y is replaced by B. So again, they unify, and because we can make them identical through a substitution. Now let's look at this one, which is a bit more critical. No, we cannot replace constants, right? Constants are only variables can be replaced. Okay, so here we have P of XX and P of AB. And the answer is no. Why? Because we have to make a choice. Either we replace X with A, and in that case, we have P of AA on this side and P of AB on this other side, or we replace X with B, and we have P of BB and P of AB, which again, they're not identical. There are no other options in order to replace X with something that will eventually make the two expressions identical. Okay, so based on these examples, now we have some sort of understanding of what is unification. And as I said, this will be enough in order to follow our first discussion with variables. Okay, so let me now move to what I have been anticipating as the abstract interpreter. How does PROLOG compute the answer to the program? So we have in input a query or goal and the program or knowledge base, if you wish. What are we going to get as an answer from a PROLOG, the execution of a PROLOG program from a query? Well, we are going to get an instance of the goal, which is a consequence which follows from the program, if this is indeed the case. In particular, if there is an instance of the goal when there are variables that follows from the program. Otherwise, we get no. Okay? Does PROLOG have a way to declare names as variables of content? No, it's just the syntax. Lowercase letter, constants. Uppercase letter, variables. Okay, now let me show you how the answer is computed. The PROLOG will be executing the following algorithm. It starts with by considering the goal, and actually all the program, all the execution is based on this data structure that here we call R, standing for resolvent. Again, this should be taken as a comment in the code. Then we use these variables to break the loop, where the loop is inside this part. The idea what is that is in this section that we are going to explore next, we want to prove whether the goal follows from the program. Okay? If we obtain the empty resolvent, not to be confused with the empty clause. So if we end up by proving everything that was requested in the goal, then we return the goal, or better, the instance of the goal. Otherwise, we return no, which means that not everything that was in the resolvent is proved. The resolvent is, it's a data structure that we are going to use in this abstract interpreter. This data structure is initialized with the goal. Essentially, is a structure which is recording all the atoms that still need to be proven. Okay? So initially, to be proven is the goal only. It can be one single atom, or it can be a set of atoms. Okay? So that's, relatively straightforward. We have the goal in the resolvent. We have a loop which operates on the resolvent until either it stops with a non-empty resolvent, or it stops with an empty resolvent. If the resolvent is empty, then we can return the answer yes and the instance of the goal. If the resolvent is non-empty, then we return no. Now let's see how we can phrase the key part, the core part of this algorithm, which is prove the goal in the resolvent. Here we go. The cycle is while the resolvent is not empty, but there is another termination condition, which is going to be controlled by this variable finished. Okay, let's first look at this, this variable finished. When is this going to be finished? Well, the finish variable becomes true here in the loop when we have disclosed that there is no more choices. We'll see in a second what are the choices, but this means that we are trying all the possible ways of building the proof. And if there are no more choices, then we close, and this closing will be with the resolvent which is non-empty. Okay, let's see now what happens if things go well, namely that we can eventually prove everything that is in the resolvent. So we start by choosing a goal, and then once we have chosen as I said, the resolvent contains a set of atoms to be proven. So here we choose one of them. And then given this atom, we look in the program and we look for a clause, which eventually takes this form. It's a rule, or it can be a fact. Let's see what happens if it is a rule. First, we need to make sure that in order to choose this clause, we find a clause such that the goal that we want to prove, A, unifies with the head of the clause, with the conclusion of our implication. And they don't have to be identical, but it is sufficient that we find the substitution that makes identical. And this is what this unify A prime means. So we look in the program, we look for a clause such that the head of the clause unifies with the goal that we have to prove. So if there are no more choices, means that we have been trying all the possible clauses, okay? Now, if we still have, we can still go on. We then replace A, which is the goal that we want to prove, in the resolvent. We replace it with B1, Bn. So we are actually doing a proof backwards. Remember that the head of a clause is the consequent, and we say the consequent is true if we can prove all of the antecedents, which they're going to be the body of the clause here. Okay, then we do the substitution, and we apply the substitution. Namely, we want to make sure that any variables that is in the resolvent and in the goal is replaced by the as requested by the substitution. And we keep looping here until we find an empty resolvent. Okay? Now, here is the structure, and I want to show you in one example. Well, we need a few more definition, and then hopefully we can make an example if it's not too late. Let me go through the few more definition. This algorithm chooses, starts with the root, can be represented as a search tree, because in fact, this is a an algorithm that tries to search for a proof of the goal, okay? So we start from a root where we place the initial goal, and then we build a tree by adding a successor every time there is a clause that whose head unifies with the goal in the node. So we choose a goal, and for each goal, for that goal, we take any possible clause that unifies with it. Okay, then we every time we choose a clause, we have to put all the antecedent in the resolvent. Okay, so every successor has a resolvent which is obtained by the parent node by replacing the chosen goal with the body of the clause. And we have to apply the unifier. Therefore, we have a tree where every node contains a resolvent. If the resolvent is empty, we can report success. We have a success node. And if we have a node with a non-empty resolvent and where we cannot move further, we have this is a failure node. Every success node represents a solution, and if there are no solutions in the tree, then we have a failure. Okay. I think maybe it's better if I show you one example. And through the example, we will make a comment on this. Okay, so example. This is the grandfather. Okay, I hope you like my drawings. So this is the root of the tree. Okay, here I have the goal, grandfather Heriberto Michela. Can you read that? Well, from this, we look for the program. Remember here, we have our program is here. We have grandfather XY, XZ, if father XY, father YZ. Okay, so what happens? We have grandfather Heriberto Michela, which we unify with grandfather XZ. So if we take X Heriberto and this is a Z. Z equal Michela. Then we have that we have to show that father Heriberto Y and father Y Michela. What have we done here in order to generate this? Well, here we have chosen this particular clause in the program. We have found a unifier, and then we have replaced in the resolvent this goal, grandfather Heriberto Michela, with the two goals, father Heriberto Y and father Y Michela, exactly the two goals that we have found here in the body of the clause. Okay? At this point, we pick up the first one, this one, from this node, and then we look into our program if there is something that unifies with this program. In this particular case, since his father is one of the relations that is in our database, we find father Daniele Michela, and therefore we can replace Heriberto Daniele, and we can replace Y with Daniele, and then eliminate this from the resolvent. When we unify with the rule, then we have to add the body of the rule. But when we match with the fact, we can simply remove the goal from the resolvent. So we are left here with proving Father Daniele Michela, which is here the obtained by replacing this Y with Daniele, which is the substitution that we have found in order to apply this fact and remove this from the resolvent. Then we are left with Father Daniele Michela, and this Father Daniele Michela is one of the facts in my program, and therefore I close with the empty resolvent here. Having closed with the empty resolvent means that this follows from our program. Okay, I understand that this example will not be enough in order to fully gather all this execution of PROLOG program, but I think it's a good starting basis for the exercises that will be given for next week. I recommend that you download the PROLOG system. As you see, it's a simple application that you get the binary and it simply runs in your shell. As I mentioned, it runs on every system, or you can also run it online, but that you practice with the writing of PROLOG programs. Write the program for your family and test several other relationships in addition to the ones that we have seen in class. Okay, I think I have to stop here, and I will see some of you tomorrow and the rest of you next week on Monday. Make sure that you start doing the exercises that I will post on the web for the material from this week on propositional logic, and to some extent also on PROLOG. Any question before we close? Questions? Okay, let me start closing